Okay, so we're going to look at another aspect of gravity with energies and that type of stuff. One of the coolest things about it. Here we got they've got the Earth, we got a rocket ship, and of course we got the rocket ship. And as the rocket ship flies away from the Earth, it has potential energy here, and as it goes further away from the Earth, it's got less and less and less potential energy. Now, depending on how fast it goes, it dictates how far it can go, because the change in kinetic is equal to the change in potential. So if it only has like a little bit of kinetic energy, its potential energy can only change a little bit. But the more and more kinetic energy you have to start off with, the more the potential energy can change. Now, ideally speaking, if you could make this, any situation you want and idealize things, what if you could have enough kinetic energy that the Earth can never pull you back? Okay, so what if, over here we've got, we have potential energy over here. So here we got potential energy, and of course, as the ship takes off, we have a change in potential energy. We've also got a change in kinetic energy, and those two are going to be equal to each other. So what if we took this? What if we took off with enough kinetic energy to get rid of all of our potential energy? Like suppose we had 1,000 joules of potential energy when we're sitting on the surface of the planet, and we took off with 1,000 joules of kinetic energy. Well, if we started with 1,000 joules of potential energy and we magically took off instantaneously with 1,000 joules of kinetic energy, well, as we get further and further away, eventually the potential energy would be equal to zero, because the change in potential will be equal to the change in kinetic. We could actually, as we move farther away, we could actually lose all of our potential energy. And if that was true, if there's no potential energy left, then the Earth couldn't pull us back. So the idea would be try and take off with kinetic energy either greater than or equal to the potential energy that we start with over here. And if that's true, then the Earth actually can't pull you back. Okay. Now, this is what sometimes people often refer to as escape velocity, and you may have heard of the term escape velocity before, especially with space-type stuff. Having an escape velocity big enough to escape the gravitational attraction of a planet or something like that. Well, if we look at this, suppose you take off, and you take off with kinetic energy, 1/2 mv squared, and what you want is this to be at least equal to the potential energy that you start with. So, of course, if you're on the surface of the planet, your potential energy would be gmm over r, and you take off with kinetic energy equal to that, then it can't pull you back. And if that's true, then this is then what's called escape velocity. Now, it's kind of cool because, once again, the masses cancel off for the spaceship. It has nothing to do with it. So it doesn't matter what you are. If you want to escape from the surface of a planet, you have to travel the same speed no matter what you are. So if you rearrange this a little bit, we get v escape. We'll just take the 2 the other side. We have 2 gm over r, and don't forget to square root it. And once we have this, we can calculate the speed that's required to escape any object we want from any distance that we want. It doesn't make any difference. So you put the 2 in there, you put the g in there, you put in the mass of the Earth, and you divide it by the radius of the Earth, because you start on the surface, and square root, you can get about 11,000 meters per second. So if you could magically jump off of the surface of the Earth at 11,000 meters per second, you would go into space and keep on going, and the Earth could never actually pull you back. And of course, different things like the moon would have a smaller escape velocity, the sun would have a larger one, but that's the idea behind escape velocity. So it's really kind of cool and something they have to take into consideration when they have things landing on different things in space and they want them to be able to get away. Okay, so 11,000 meters per second is really, really quick, and of course, an instantaneous speed like that's impossible. But trying to have like the space shuttle or rockets trying to accelerate to a speed, kind of close to that would then allow them to maybe get into space. And of course, the further you get away from the planet, your radius is going to keep on getting bigger, which means the speed you need to reach to escape actually becomes smaller as you go further away, which kind of makes sense. Okay, so that's the idea behind escape velocity. So it's pretty easy to calculate the escape velocity for pretty much anything. Now, one of my other favorite aspects of this is a little bit different. So let's see if we can clean this up a little bit. We'll get rid of, let's get rid of all this here. Let's get rid of this. And, oh, it didn't work. Let's try again. We're going to get rid of all this stuff. Like that. There we go. And we're going to be left with this. And we'll just get rid of this as well. All right. Okay. So the idea behind escape velocity is pretty simple. You know, have enough kinetic energy to cancel off the potential energy you have at whatever object you're at. Well, what if we specialize this a little bit? What if we specialize this? What if instead we don't take any speed and just any random tangible speed? What if we modified this and made this the speed of light? What if the escape velocity was the speed of light? Well, this kicks into something else, of course. If you're talking about having to travel the speed of light in order to get away from something, this is the token idea behind black holes. So this is where black holes can kick in by using this idea. So if you have something with a mass and radius such that when you do this calculation, this gives you the speed of light, that is then a black hole. And it sounds like a really complicated, fancy thing, but it's actually a relatively simple-ish idea. And you can actually use this expression to then calculate how big a black hole could be, depending on the mass of the object. Because black holes don't have a specific mass or radius per se, it's the ratio actually right here. It's the mass divided by a size thing. It's like a density type thing more than anything else. So you could actually use this idea to calculate how big things would have to be in order to be a black hole. So if I go back to the original expression up here, which is basically V escape squared divided by 2 is equal to gm over r. I'm just going to undo this part over here. I can actually change this a little bit. I'm going to get rid of this v here. I'm going to change it to the speed of light squared. And what I could do is I could actually calculate maybe the Earth. How big would the Earth have to be in order to become a black hole? So the radius of the black hole would then just be 2gm divided by c squared. Okay, it's just rearranging. So if I take, I got the 2, I got the g, I put in the mass of the Earth and divide it by c squared, I can calculate the radius of the Earth if it was a black hole. So let's see, rounding off a little bit, that's about 8.8 millimeters. Okay, so that's, it's almost a centimeter, and if we double that, to get the diameter, if we look at the Earth as a black hole, well, if you took the exact same mass and you actually put it together, it would be, if you double it, we'll say it's around 1.8 centimeters wide is how big it would be. Now, on my computer screen, that would be about, let's see, I'll use this guy right here. Well, all computer screens are different, but about that big. Okay, so if the Earth was actually that big, about 2 centimeters wide, it would be a black hole. Okay, so it's kind of a neat way, because some people talk about black holes being infinitely small. Well, that's one way to look at it, but using this idea, they can actually calculate how big black holes could be. And you'll often hear them talk about supermassive black holes at the center of galaxies. And when they mean massive, it's not just heavy, but also they can be rather large. And you can actually use this simple calculation and the simple idea of potential energies in order to calculate approximately how big these black holes could actually be. So this is one of my favorite type of applications of using energies and gravity and that type of stuff.